All right, everybody, thank you for your time. We're ready to begin. This is part of our sustainable and printed circuit board electronics tech topic series. We are fortunate today to have two presenters. We have Maarten Cauwe from imec, who's going to be talking about LCA models for assessing and improving the environmental impact of PCB assemblies. And we also have Jack Herring from Jiva, who's going to be talking about transforming electronics with recyclable PCB technology. I do want to let everybody know that you are on mute, and I would ask that you please use the chat function to ask any questions. We are going to hold all the questions until the end of the session, so after both presenters have a chance to present. We will try to monitor the chat, and if there are questions that come up that need immediate response, I will try to interrupt and get those answered. But by and large, the goal is to collect all the questions and ask them at the end. Do want to let you know that the slides and the recording of this session will be sent out to all of the registrants. So thank you for joining us. And this is a joint meeting of the INEMI Sustainable Electronics TIG and also the INEMI PCB TIG. The Sustainable Electronics TIG meets pretty regularly, second Wednesdays of each month from 11 a.m. to noon. If you're interested in joining us, please drop me a note if you do need to be an INEMI member. Our next call is on July 9th, and it's going to feature speakers from MIT, which are going to be talking about sort of workforce development as it relates to the kind of sustainability knowledge that they need, that they're finding that people want to have. And then also the PCB TIG meets, I think, in a couple of weeks, and they're working on a survey regarding some potential project areas. And I would ask you to reach out to Emma Hudson, who leads that activity, if you'd like to participate either in the TIG or in the survey. And our contact information is here. However, you're not here to hear my voice. You're here to listen to Jack and to Maarten. So I'm going to turn it over to Maarten. So if you'd like to share your screen, we can let you run. We got about half an hour or so for you. I will try to monitor the time and let you know.
Okay, sounds good. So my name is Maarten Cauwe. I work as an R&D team leader at imec. I have a background in packaging and PCB technology, and I apply that background to medical packaging, high reliability markets, and sustainability, which is the topic of today. Together with my co-author Geert Willems, who's also present here, we have developed some LCI models for printed circuit board manufacturing and printed circuit board assembly. And I'm happy to share with you the details of these models. So when we speak about sustainability of electronics, initially the focus was on quantifying the impact of the electronics. So what we call assessing the situation. We want to identify hotspots. And for this exercise, as many of you are aware, there's a challenge with getting the correct data for electronics. This assessment activity is typically driven by reporting obligations. And while not everybody needs to do this reporting, typically large end users are obliged to do so, and then this trickles down the supply chain, which is why also for those companies, these LCA data models become relevant. Of course, we don't only want to assess the situation, we also want to improve it. So we want to reduce the impact of electronics, but we want to do so without so-called burden shifting. So when we improve on one impact category, we get a negative influence on another impact category. So this improvement is done through eco-design. Eco-design is basically from the design stage, taking into consideration the environmental aspects. And this is done through, taking into account the entire product life cycle. However, in the context of this presentation, I will be speaking about eco-design mainly as an impact on the manufacturing process, so electronics production. What's the problem? LCI data, and with that we mean energy usage, water usage, how much materials, what waste is generated, etc. For electronics in general, in the best case, it's incomplete data or outdated, but in the worst case, it's just not available at all. As I mentioned, both regulatory observations, but also general environmental concerns and market demands push end users to collect this data for their products, and they go down to the component IC and PCB suppliers to get that data. What's the ultimate solution we would like to have in the electronics industry? And that each and every component has a so-called eco-passport or this digital passport. This is prepared by the supplier and then handed down as the product goes through the supply chain. So for example, for a printed circuit board assembly, you would have an eco-passport for the PCB, for any active components that are on there, and also for passive components. And then this printed board assembly would collect all of these and then hand it down to the equipment supplier, which again hands it down to the system composer, which in this case would gather a full eco-passport for a satellite. For those less familiar with life cycle assessment, basically what you do is you look at the entire life cycle of a product. And for that, you do two things. First of all, what we call life cycle inventory. So you gather and quantify all the inputs and outputs for a given product. And then for all those inputs and outputs, you determine the impact in the so-called life cycle impact assessment. And combined, this gives you the total life cycle assessment. For this presentation, I will focus on the life cycle inventory part, which is one of the key components to have for the determination of the sustainability impact of electronics. What we try to do at imec is to facilitate data collection for electronics manufacturing. And we do that by so-called introducing parametric LCI studies. It's a concept that not only is applied at imec, several groups follow this reasoning. Basically, the idea is to move away from these static aggregated records that you can find in many LCA databases and have LCA models that are dependent on the design. So they design input and then translate that design input onto the production process, resulting in an LCI information for your specific product, printed circuit board, component, or assembly that you're creating. The principle is implemented by two different subcomponents. First of all, we have what we call manufactured system elements. So these elements are manufactured more or less from raw materials, and the manufacturing process combines typically water and energy with some auxiliary materials, and then in the process there is waste generated, materials are lost. Then several of these manufactured system elements are combined into what we call an assembled system element, and this assembled system element in itself can also consist of again, assembled system elements. So in this way, we can go through the hierarchy of a system and at each level compile the relevant LCI data and end up with a complete system LCI. An example I like to show, and that some of you will probably have already seen, is if we have this chair with notepad as an assembled system, we can divide it into its manufactured system elements, being the plastic of the chair, the metal frame, and then the wooden tablet. And this wooden tablet is made obviously from wood. There's a process in creating it. There's some sanding paper used as an auxiliary material. The remaining wood that is not part is waste, and then we end up with the product. In a similar way, we can do this for electronics, being it the onboard computer of a satellite, data center server rack, or a mobile phone. Each of these consists of printed circuit board assemblies, which themselves again consist of the printed circuit board, the electronic components that are put on there, some assembly materials, and then some mechanics. The electronic components, again, can be further broken down into passive components, connectors, and then active components. And typically, the active components consist of an IC in an electronic package. So at imec, we have been developing parametric LCI models for each of these various stages in the from an electronic system. So we have a model that is looking at semiconductor manufacturing and quantifying the electronic impact for various semiconductor nodes. Recently, this has been expanded into component packaging. Both of them are available through the imec Net Zero app, which I will come back in a moment. However, for today's presentation, we are looking at our LCI models for printed circuit board manufacturing and printed circuit board assembly. So as you can see, at imec, we are offering models for each step in the supply chain. And by combining these models, we can do a full assessment of the electronics manufacturing. As I mentioned, for today, I will focus on the printed circuit board and the printed board assembly part. No matter which part we're focusing on, the IC manufacturing or the PCB manufacturing, they more or less all operate in the same way. It's a kind of virtual fab model where we focus on the electronics manufacturing. We took into account some material sourcing in the sense that we calculate the material use. We're not looking at the product phase, use phase, or end of life, but we're focusing on the manufacturing part. Now, at imec, as I mentioned, we're developing these models, and most of them are part of the Sustainable Semiconductor Technology and System program. This is a program running at imec since 3 years now, or a little bit more. And it's a combination of system companies, fabs, equipment suppliers, material suppliers that are working on these various LCI models. If you're interested in joining this program, feel free to reach out. This program also has or creates an app that we're calling imec.net Zero. This allows you to dig into the different impact category, or let's say impacts of the electronics manufacturing. At this moment, IC manufacturing and packaging. There's also a public version of that is freely accessible. So if you go to the link that is included in the slides, you can register and access the public version of imec Net Zero. Now, as I mentioned, I want to focus on the printed circuit board manufacturing. And what we did here is we built an LCI model at this point for multi-layer PCB manufacturing. So we have the let's say high level process flow where we start with the inner layer processing, laminate all the inner layers together. Then we do the drilling, metallization, patterning of the outer layers, and apply finishing, surface finish, and the solder mask. And at each of these steps, we take into account the energy consumption, water use, waste generated, and then also the various auxiliary materials that are used, like, for example, photoresist or press pads, backup material for the drilling. and also input materials, obviously, along the way, going from the base material, copper foil, to the copper that is added during plating, or materials for surface finish and solder mask. As an input to the model, we're using the buildup of the PCB, obviously the size, type of materials that are used. We can take into account the exact layout and the type of surface finish. The model calculates the material content of the PCB. We can do that based on the design files, but we can also use a more high-level estimation of the amount of copper per layer, depending on where you are in the design process. If you're still early, you can do an assessment of the material usage already just based on that. Important to note here is that the PCBs are manufactured on large production panels, and only part of that space is used as a usable area. So this is taken into account by the panel occupation. So basically the number of PCBs you can put on a panel. The process data, the process flow I just showed you is broken down into individual process steps. And then for each of these process steps, we calculate the energy consumption, water use, chemicals that are used, and the waste that is generated. And we do that based on the line speed of the throughput of the process. Basically, for the chemicals, we take into account concentration of the chemicals used, and obviously we during processing only calculate that for the real area of the PCB that is used in the end. An important aspect in our LCI models is that we want to have a straightforward way of collecting the data. In this case, we want to collect the data from the PCB manufacturer, so the details of the process, and we strive to do that by requesting data that is more or less readily available from that PCB manufacturer. So we're taking the production volume in panels per year into account, the line capacity, installed power of the equipment, then the water usage per line, main chemical that are used, and then the waste product that is generated. Of course, if you collect this information for a PCB manufacturer that has a low volume, high mix kind of production versus a low mix, high volume, this will obviously give you different numbers. And at this point in time, we do not consider yield per process step in the model. However, we can easily apply an overall production yield. This method is obviously not as accurate as you would really go and measure, for example, the energy consumption or the water use. However, it makes it much more easy for a PCB manufacturer to collect the data, so it's easier to request this data from multiple sources, from multiple manufacturers, and also it doesn't require much overhead from the PCB manufacturer. So showing some output of the model, first of all, the material contents. So we calculate how much material is used in general, how much ends up on the PCB, and then the difference between that is obviously the waste. We can do that based on a percentage estimation, but we can also do that based on the design, as I already mentioned. As you can see, in this case, we have a 60% panel occupation, so we're losing quite a lot of material that is in fact not ending up at the PCB. If we compare our estimations based in the model on those percentages with the actual design calculation, we see that we're not that far off, except for the copper foil calculation for the inner layers. which is obviously related to the percentage of copper you have on those layers. Important to highlight here also is that for about 100 grams of PCB, you need quite a lot of these auxiliary materials, especially aluminum and wood backing material for the drilling. So these can be quite significant contributors to the waste that is generated. Looking at energy consumption for a 12-layer PCB with an imec finish, our model predicts about 2.5 kilowatt hours of energy consumption. And we see that the through-hole metallization, the outer layer processing, patterning, and the inner layer processing are the main contributors to the energy. If you compare that to the primary data from the same manufacturer, then you see that the same three contributors are coming again as the prime contributors, sorry. So our model in that sense is aligned with primary data. The reason the metallization processes and the outer layer patterning are such a huge contributor is because these are quite slow throughput processes, requiring a lot of energy, and as you will see, also a lot of water. So looking at the water, we have water use on the one hand, tap water or soft water, on the other hand, deionized water. The deionized water is mainly used to prepare chemicals and for some rinsing processes, while the majority of rinsing processes is done using tap water, mainly for the plating processes. The inner layer processing is using the majority of the eye water because this is in this case used for rinsing. And obviously for a 12-layer board, we have 10 inner layers, so 5 laminates that go through the inner layer processing. So in general, it's very difficult to determine the accuracy of a life cycle inventory model. It's challenging to do comparison with different models because each model uses their own scope. Some models take into account materials, others do not, for example. Also, the metrics that are reported vary strongly between models, and some models are even confidential, so they do not share the details, which makes it difficult to compare. I think our model should be seen in the light that it's mainly or initially intended as a kind of proof of concept model. As I said, an important limitation was, can we use data that is relatively readily available to do a fairly accurate estimation? And we believe we can. Of course, we need to further expand on this model, including more data from various PCB manufacturers, and then also expand it to other PCB technology like flex PCB production and also HDI PCBs. We have a similar model for electronic assembly. I will not go into details, but basically it covers your typical assembly flow, starting with the surface mount assembly at the top and bottom part, and then through-hole assembly. This can be wave soldering, manual soldering, selective soldering. And then in the end, there's some cleaning processes. And here we consider the full bill of materials as a design input, and obviously also the type of materials that are used for the assembly and the layout of the PCB. So it's still a challenge to collect all that data for PCB manufacturing and assembly. Most data sets that are out there rely on these static fixed data sets, which is not suitable, I think, for electronics manufacturing. These parametric LCI models for PCB assembly can take into account the design data, and they give sufficiently accurate estimates. While we collect data in the simplified form, of course, there's always a consideration on the source of these data, depending on you get it from, as I mentioned, low volume, high mix, or a high volume manufacturing model. But in the end, we believe that these parametric LCI models can be used for eco-design, so they can be implemented in design tools to give feedback to the designer about the environmental impact. So to provide a bit more detail on that eco-design part, our model typically generates LCI data. So we have material, water, energy, and waste. This can be combined with an impact assessment to do life cycle assessment, as I mentioned before, which is then suitable for eco-reporting. However, you can also use this LCI data to optimize your design in such a way that you reduce material use or reduce energy. And in this case, it can be used for eco-design. Now, if you look at sustainability as a design driver, we can take into consideration certain design aspects of the PCB. First of all, the size of the PCB. These is typically defined either by the housing where the PCB will end up in, or the amount of components that need to fit on the PCB. As I mentioned before, PCBs are produced on large panels, and obviously the more PCBs you can fit on a panel, the lower the impact per PCB, which in fact is also the case for cost. So in this case, cost effectiveness is also better for the environment. Now, if we consider not only the size, but of the number of layers, typically the build of a PCB is determined by the final functionality that it needs, the performance it needs to attain, and then also the routing density, because you need to route all the connections between the components. And this then typically defines your buildup. However, if we would look at sustainability as a design driver, then we see that we can quite significantly impact, for example, energy use. I took here a 4-layer PCB, which has 2 signal layers and 2 ground layers, and let's say it fits 4 times on a panel. According to our model, it's about 4 kilowatt-hours per PCB. Now, if you would redesign that PCB into an 8-layer PCB, double the amount of signal and ground layers, and ensure that it fits, so make it smaller and that it fits 9 times on the panel, you can reduce the energy need for manufacturing that PCB by more than 50%. Of course, there are some cases where this is not feasible, but it just illustrates that, okay, if you optimize for environmental impact, you can really reduce the impact of the PCB. Another area where huge improvements are possible is the surface finish. So the energy consumption and the water use per PCB vary greatly for the process from surface finish to surface finish. If you're familiar with processing for PCB's surface finish, you can understand that a much more complex process like electrous nickel immersion gold has a much higher need than a simple hot or surface level of our thin lead finishing process. However, it's not only the process itself impact that makes a huge difference, but in fact the presence of that gold in that imec surface finish. So despite the fact that there's only 100 nanometer of gold, typically on an INIC finish. For every 5 square centimeter of INIC, you have 1 milligram of gold, and gold has a huge so-called embodied energy, so the energy needed to produce that gold, which is for that 1 milligram of gold already 15 grams of CO2 equivalent. If we go back to our 12-layer PCB, which has a total surface area of 220 square centimeters, a little over 100 square centimeters of that is INIC surface finish. So it has about 21 milligrams of gold, which is equivalent to about 1.5 kilowatt hours of embodied energy. So here it's 2/3 of the energy needed to produce that PCB. Clear, I think obvious recommendation is here, avoid the use of noble metals in your surface finish, because these have a quite huge impact on the environment. And then finally, something that is also overlooked, the best energy or the most environmentally friendly energy is the energy you don't use. What you see typically for designers is they like to design with the smallest features or the smallest via size, using top-of-the-line surface finishing, specifying reliability classes for their PCBs, which in fact are not needed. These leads typically to reduced yield, scrapping of samples, unnecessary process steps. So also here, reducing, giving feedback to the designers about the impact of their design choices is very helpful to reduce environmental impact. So in conclusion, while there's no magical solution for reducing the impact of PCB manufacturing, there are a number of design measures you can take. Most of them are aligned with the cost reduction, so that's a positive. And the most tangible advice is, if you don't need gold-based solderable surface finish, please don't use that. Obviously, designed for manufacturing, designed for reliability, will improve production yield, extend the lifetime of your product. So these will also benefit the environment. I haven't discussed design for recycling for two reasons. It's more relevant at printed circuit board assembly than for bare PCBs. In fact, that's the main reason why we didn't discuss it. Number of PCBs per panel, production yield, and the choice of surface finish, as I mentioned, have the biggest impact on the amount of energy, water, waste generated, etc. And we plan to further expand our PCB LCI models and try to integrate them in the design flow, and preferably into the design software, so that immediate feedback can be given to the designer. Oh, sorry. And with that, I come to the end of my presentation. I would like to thank the members of the SSTS team at imec, obviously my co-author Geert Willems, and then also Eddie Herings from ACB and Dendermonde, who helped collect data for the initial model. The initial model was made during an ESA project where we worked together with OHB and Vito. So I would like to acknowledge their contribution here as well. And with that, I'm at the end of my presentation, and I think I can hand it over to Jack.
Thank you, Maarten. There is one question in the chat for you. Maybe you can take a stab at it in writing if you'd like. If not, we'll let everybody ask questions after Jack finishes his presentation. So Jack, let me turn it over to you.
Great, thanks Mark. Thank you, Maarten. Just loading the file up now. I think we tend to bump into each other a lot of these, Martin. So there's a lot in common in terms of what you have just talked about and what I'll be going into. But I think it's a nice segue to take the existing manufacturing process through to our material, because that's a big part of what we've been designing our technology for. So sorry, it's just taking a while to load up.
I was just going to say that's the only reason I'm here, to introduce you, basically.
You did a great job, Martin.
My name is Jack Herring. I'm the founder of Jiva. I'm here today to talk about our recyclable PCB technology. We're the creators of Soluboard, which is the world's first fully recyclable and biodegradable PCB laminate. So I'm here to talk you through exactly what our mission is, and how we're reshaping the way that we should think about sustainability in electronics. So everyone in the room is probably aware PCBs are made of fiberglass and epoxy resin, typically for rigid laminates. And when recycled, they're typically incinerated to extract precious metals at end of life. So we've developed a material that allows PCBs to be recycled in a cleaner way, as well as reducing the carbon footprint. So we're based in Hampshire in the UK. We've been developing sustainable materials since 2017, and our product is biodegradable. Big thing to consider is that it's a thermoplastic based laminate, which is disrupting the traditional epoxy fiberglass composite used in the PCB industry. So not only does it reduce the carbon footprint by 68%, we're also enabling a truly circular electronics economy. So I'm very fortunate to work with a lot of gurus in the industry, and you'll be familiar with one of those or at least one of those faces on there. So you've got Steve Driver, who's the CEO. We're also working with Alina for business development. Erdem is our material scientist, and we have access to the University of Portsmouth's testing facilities through him. And we're also working with Alan Morgan and Emma Hudson, of course, as our UL advisor. So PCBs are the hidden infrastructure of modern electronics, and by 2030 we're actually expected to generate 6.5 million tons of this PCB waste every year. So this is not just PCBs at end of life, but it also includes a waste stream, which Martin referenced in terms of the way that PCBs are panelized. So there's a huge amount of waste just from the frames of PCB manufacturing. So this e-waste crisis is accelerating, and we're expected to exceed 82 million tons by 2030. There's also lots of regulatory pressures which are influencing the carbon footprint demands and carbon accountability from electronics OEMs. So the industry urgently needs an alternative. So our solution, Soluboard, offers a revolutionary alternative to conventional epoxy fiberglass. Our carbon footprint is lower than FR-4. Actually, we've just exceeded the 68% that I have here. We're up to 70% now. And our material has been designed to be a drop-in replacement, meaning that it can seamlessly integrate into a PCB fabrication process. That means that all the research that Martin's done is still relevant for the processing of our material. Our material can also be recycled without the need for harsh chemicals. This is a certified non-hazardous hot water-based process, and this allows both the recovery of precious metals, but also moves us towards a circular economy. So a bit about our journey so far. We started in printed electronics. I invented the material at university back in 2017. Got some funding to start a company. And we've taken the product all the way through from printed electronics through to compatibility with copper-clad laminate production. We can now successfully produce plated through holes with our material, and we're working towards multi-layer compatibility later on in the year. So we have quite a wide portfolio of products, but they're predominantly segmented into two halves. So you have a jute pre-preg and a flax pre-preg, although we are exploring other alternative raw materials as well. We can produce our material just as bare laminate, so we can be compatible with the printing industry, but typically we supply our material as a copper-clad laminate. So we're not trying to replace everything that's on the market. We're aware of all of the offerings, all of the different laminates that an OEM can choose from when they're specifying a PCB. If you're looking for a very versatile material, you might look at the likes of FR-4, but if you're slightly more subject to low costs, FR-2 or SEM1 would be a choice. Flexible circuits, you've got PETs, polyamides for signal integrity, you've got ceramics and PTFE. Heat dissipation, you might look at an aluminium based board, but we would like to be the material of choice if you're driven by reduced CO2 impacts or ESG regulatory influences. So our USP is our reduced carbon footprints, although our material can be recycled at end of life. This is mainly for single-sided applications. So here you can see an example of a LED lighting board which is going through the process. At the end of life, the precious metals and the copper can be recovered in a more concentrated waste stream, and then the natural fibers can be sent for composting, and the wastewater is non-hazardous. So this has been certified by Envirochem in the UK. And our wastewater off the back of this recycling process can be discharged to the standard effluent treatment plants. Our next step of this waste certification is to get our solid waste confirmed as being non-hazardous, but we don't have any concerns there. So a big part of our product is the way that we make it as well. So we're actually producing our material using a dry process as opposed to the standard impregnation of epoxy and fiberglass with treatment towers. And so we're using a belt press process, which is using heat and pressure to produce the bare laminates. We impregnate our natural fibers with our polymer blends, with our phosphorus-based flame retardants, and we can then apply copper foil to the material, just making a continuous one-step process. So expanding upon the LCA for our material itself, here you can see our calculations for Soluboard 1.6mm version. So in these calculations, we assume the raw materials, the processing costs, and the transport, and you can see for each of those we have a significant reduction over FR4. We also have even a larger improvement for a 0.4mm version of the material, and we also offer downstream benefits from using our material. So as I mentioned earlier, we're a thermoplastic, and we do suggest that our material is assembled using low temperature solder. Switching from a 265-degree reflow oven to 170 degrees reduces energy use by 40%. That's about a $9,000 cost saving annually per oven, and you're also saving 57 tons of CO2 per oven as well. But we have to look at the impact that our material has on an assembled product, and that takes into account the work that Maarten does as well. But for example, one of the applications we were looking at is a laptop, and 68% of a laptop's carbon footprint comes from its PCBs. So that does include the processing as well. But just by switching our laminate out, so from FR4 to Soluboard, 3.5 million laptop trackpad PCBs, which is one of the proofs of concepts that we've done, would actually remove 1.57 million kilos of CO2. Very similar case for Amazon. They're looking to be net zero by 2040. This is for a power supply. This is a standard LED lighting board. LED lighting is very, very ESG driven, and they're looking to source alternative materials of reduced carbon footprints. And this is a battery controller we've made for Webasto. As you can imagine, the automotive industry is very quickly moving towards sustainable materials. So we're now certified to ISO 9001, and we have IP all across the world, including the UK, US, and all over Asia. But we're now looking to further develop our supply chain outside of Europe. If we look at other offerings on the market, you have two main options really to consider. So you have the recycled material, which is a product being developed by Shengyi, a big Chinese laminate manufacturer. This is essentially an FR-4 with a degradable hardener, although it does require a very harsh solvent to recycle at end of life. So paper shell is another alternative. Paper shell is based on the paper, as the name suggests. This is coming out of Sweden, which is very the paper industry is a big thing in Sweden. So this is quite early TRL, and they haven't yet validated the life cycle assessment. So if we look at the properties of the material, another point of interest for our users is our lower density. We're 37% lighter than the likes of FR4. We also have a lower CTE than FR4. We're actually thinking that this might enhance our dimensional stability compared to other rigid laminates, and I'll expand on that in a couple of slides time. We have a slightly lower dielectric constant than FR4, but we are still compatible with high frequency applications where we're still okay for Bluetooth and Wi-Fi use. Thermal conductivity, we have essentially the same properties as FR4. Flammability rating, we're currently at a V1, although the more recent iterations of our material, we're now securing V0, and we're looking to resubmit soon. We do have quite a low TG compared to the likes of FR4. This is because we're using a thermoplastic matrix, but we're not cross-linking anything. So this is one of the compromises that we have to use with our material, but that's why we suggest that people use the low temperature soldering process, which also offers environmental benefits as well. So one of the tests that not everyone is aware of, if you're not familiar with working thermoplastics, is the ball pressure test. This test essentially confirms that a material is able to withstand mechanical stress at higher temperatures, and it involves a 5mm steel ball being applied at 20 newtons at 125 degrees C for 20 minutes. It took us a long time to actually pass this test due to the polymer that we're using, but we've done lots of engineering on the various iterations of our material, and we now continuously pass this test, not exceeding the 2mm impression, which is the point of passing. If we look at the CTE that I mentioned earlier, we've benchmarked our material against 3 different FR4 samples from various suppliers. Typically the FR4 TG is 130 to 150, and thermoset material tends to observe a sharper increase compared to our material. This means that we should be less subject to expansion and contraction with our material, which can sometimes put stress on plated barrels and solder joints. So we are hoping to reduce points of failure for power electronics, which is one of the use cases for our material. As I mentioned earlier, we've got some access to some great equipment at the University of Portsmouth. We have a CT analysis machine, which is very important as we're using a different manufacturing process with our powder scattering process. We need to make sure that we're checking for voids in our material. So here you can see our natural fibers, which have been very well impregnated, and we have good consolidation with no visible voiding. And we also repeat these tests for the PCBs after the fabrication process. We've achieved good drilling on our material. We have to drop the speeds down a bit in terms of the drilling because we're using a thermoplastic, and things tend to melt a bit at lower temperatures. But you can see we're achieving good plated barrels now, and we're also able to reduce our hole size even further off the back of some testing that we've done just this week. Environmentally, a question that we get asked a lot is about the humidity and the lifespan of our material. So typically, a standard reliability test in the industry is 85 degrees Celsius at 85% relative humidity. This does affect the moisture absorption rate for our material, but we've seen that by dropping the relative humidity down to 75%, our material is actually able to perform equivalently against the likes of FR-4 and SEM1. So we're not seeing too many negative impacts of using our material, particularly as once the copper and the solder mask is applied, there's very little surface area of our raw material to actually be exposed to the humidity and the natural environment. So I've included our data sheets and our design guidelines here, which will be shared with these slides after this webinar. But a lot of this testing has been done with the help of the University of Portsmouth and University of Glasgow. One thing I'll touch on here is the surface finishing. We do prefer to use immersion silver, OSP. They're the two lowest in terms of the carbon footprints, but also because they use lower temperatures in terms of the application to the finished PCB. As Maarten said, processes like ENIG can be relatively high in terms of their carbon footprint as well, but also the temperature. So we have a few aligned partners. There are use cases where gold is necessary, and we're working with a US company called Lilotree. So Lilotree is able to apply gold finishing to PCB, removing the nickel-less step of the process. This step is the part of the process which causes us an issue because it's typically done at quite high temperatures. But we also see the benefits of in terms of the cost and also the energy savings of using the Lilotree process as opposed to a standard ENIG process. We've also been looking at the circularity with Lilotree as well, as they've expressed an interest of recovering our PCBs, which we successfully demonstrated as being compatible with their soldering process. Our boards could be recovered by them, the gold could be removed and reapplied to more Soluboard PCBs. So in terms of what's next for us, I mentioned at the beginning that we're looking at moving towards multi-layer, starting with 4-layer PCBs. So in order to do this, we need to decrease the thickness of our material. We're working on a thinner core. We're looking at alternative natural fibers such as hemp and lyocell, which is a more refined cellulose-based fiber, which will allow us to replicate the weaves which are typically seen with glass fibers. We're also hoping that moving towards a continuous manufacturing process will allow us to reduce our carbon footprints even further. So this is what we're currently doing. We currently have a belt press where we put the natural fibers in, impregnate them with the fiber, split the pre-preg and then consolidate it under heat and pressure in a belt press. But by being able to remove that second stage, which is currently done with the likes of a HML press and having it all continuous, we expect that we would be able to reduce, to improve our carbon footprint reduction up to 76%, which would be a big achievement. So we believe that we're the most mature challenger to the incumbent PCB materials if you're looking for something sustainable. We have a reduced carbon footprint, we're recyclable, we avoid the use of any harmful chemicals in these processes, and we think that this sustainable choice not only meets the emerging carbon mandates, but also we offer a transparent supply chain from raw materials through to finished product. So thank you for listening. If you're a designer, an OEM, you're looking to lead in electronics, then we want to work with you. Happy to take any questions. Thank you.
Thanks, Jack. Is Mark, you?
I can't hear Mark.
There you go. We can hear you
So
now.
I'm talking to
Yeah,
myself.
okay.
That is weird.
You
God
were.
bless. I love that. Anyway, so sorry about that. Please, if you have any questions, I would say we've got about really half an hour left. You're more than welcome to raise your hand in the Teams, and I'll try to unmute you. If not, there are a couple of questions in the chat that I think have been addressed already. The one that I didn't see an answer for was regarding from Jenny asking about the database that was used for the FR-4 LCA comparison. And I'm not sure if that was for Jack or if
Probably
that
more
was
relevant for me,
Martin.
I think. I think so. What we did, we actually struggled to source any accurate data from the incumbent manufacturers. So we effectively built our own LCA using the SEMA Pro system, based on the transport, the raw materials, and the processing. And we had some great advice from Alan Morgan, who's one of the PCB laminate gurus of the industry. And we've effectively built our own database for FR4 because we were struggling to find anything which was truly reliable. I'm happy to share those calculations in a bit more detail if you'd like to take a look at them. We have a full LCA report to back up the data that I presented as well.
And I think in yours I also saw you had some LCA data for low temperature solders. Was that? I know that's something that many of the INME members ask for that they can't find. So did you have to make that as well, or were you able to find some of that?
It's based on some calculations which Intel produced, but we adjusted the temperature process using their calculations, and that's effectively what we based our calculations on. But it's a third party piece of data that we've used for ourselves.
Okay, no, fair enough. That's good.
Happy to share that as well if people are interested.
Yeah, that's sure. It sounds like Jenny would love to see any additional calculations and reports. So if that's something you something you want to flash on screen, that's great. If it's something you want to share afterwards, I can get you her email so that you can directly communicate with her if you'd like.
Yeah, it's probably easier to share by email. If you could share Jenny's contact details, that would be great. Yeah.
As long as Jenny doesn't mind, we'll be fine.
Yeah, of course.
Other comments or questions? Yeah, Jenny said that's fine. So Jenny, I'll give Jack your email then afterwards. Any words from you, Emma? I know I do sustainability. Emma does printed wiring boards, so see if there's any words from Emma.
Yeah, no, they're both great presentations. It's really interesting to see what we need to be considering in PCBs. We've spoken about it during the PCB TIG, and so often it's sustainability is in one silo and PCBs are in another, and we really do need to bring those two together. And I think these sorts of things, certainly Martin and Jack are really helping us with that. So thank you both.
No problem. I think it's long overdue, and we're doing the best that we can to have the impacts that we can.
Yeah, it really is. So we were talking about it recently in the TIG, and we said, well, kind of to the PCB guys and people buying the PCBs, is how much is sustainability impacting you? And it's dependent on customer, and it's also, it seems to be often it's siloed off into one division of a company rather than actually being across the board, which I think it really does need to be now going forward. So no, it's really good. So thank you.
Any further comments or questions from anybody in the audience, or Martin or Jack, anything you would like to emphasize?
No, well, I think Martin, I'm sure we'll get to a point where we can combine both of our data sets and actually determine how our LCA will build upon our raw material. So we're currently doing cradle to gate, but ideally people want cradle to grave or cradle to cradle if you're able to adopt circularity. We're big fans of Maarten, and we look forward to seeing what we can do one day in the future.
The feeling is completely mutual, so happy to work together.
That's great. We need people working together. Collaboration is the key for really everything, not just in electronics, but definitely here in the electronics world. Change is so fast. Need to work together. All right. Maarten and Geert, do you think you've answered the questions in the chat sufficiently, or do you want to address any of those verbally? And there's also another question here. Let me read that. Great presentation, as you mentioned, about CIMA-Pro. A question on the difference between the PCB populated database, covers the PCB board and electronics components, and PCB unpopulated database, which is FR-4 PCB board. So if we analyze the impacts of both, what would be the consideration to calculate the impact of the PCBA and how the impact percentage will vary? What's the right approach to model the PCBA to calculate the accurate impact results? And that's down in the chat for those of you following.
So we use our CIMA-Pro, but we don't really look at the assembly side of things too much. I don't know if you've had any experience of using that, Maarten.
Not within CIMA-Pro. I'm struggling a bit to understand the question, but basically the right approach to model a printed circuit board assembly is to do both. Model the PCB, including all the materials there, and then model or take into account the impact of all the components and the assembly process. I don't know if that answers the question.
Yeah, you're welcome
I think
to unmute if it's not.
From our experience, CIMA-Pro is great if you go back right to the start from the point of raw materials, because a lot of the FR-4 and PCB data on there has been quite outdated up until now. So that's the reason that we decided to build our own data set, because we weren't fully convinced about what was on there in the libraries available.
Yeah, maybe if I can add something to this, because this actually touches upon what we call our paradigm shift, going from static data records, which give you LCI data on some part, like a fully populated printed board assembly or a PCB, not taking into account the large variation that you can have depending on the design. So that's where actually this static data records, which you can find in CIMA-Pro or whatever, just breaks down. You have to go down to and that's what we have done here, down to the design of the printed circuit board, down to the full bill of material, and then combine these things. And this is the input for an assembly flow, where you have also per design amount of solder paste added and energy used for populating top side, bottom side, or whatever you do there. So this detailed modeling is required to get accurate LCI information or LCI data, and not using static data records, which you can find in these databases.
Did that answer your question? If not, please unmute I can unmute you and you may converse with everybody.
I think I saw a thumbs up.
Okay, great. Any other comments or questions from anybody? If not, I can certainly let you guys go and have a little bit of your day back. Going once, going twice. I'm going to say that's gone. All right. So thank you for your attention. Speakers, thank you for joining us today. If you do have any further questions, you can email me, marques@inemi.org, and I will pass it on to the speakers. And I also will get Jack, Jenny's email to you. So,
Perfect. Thank you.
Maybe there's a hand raise. Yep, from Susanna. Are you able to unmute yourself? There you go.
Sorry, that was by accident. I can't turn it off.
You were going to applaud and you raised your hand. That's okay. Yeah. That's fine. I got it. I get it. Oh, yeah. Trust me.
You're obliged to ask the question now.
It has been brilliant to have these sort of talks, because I'm quite new to this. While trying to get into the sustainable electronics, I'm actually just started a PhD on it, and it's fantastic that there is stuff going on, because I think it is so needed.
Great.
So yes, so thank you.
Thank you very much for attending today. All right. I will give you guys about 15 minutes of your day back. So thank you so much. Maarten, Jack, Geert, thank you so much for your work on the presentations, and we'll follow up with you in the next day or two, see if there's anything else that you might need from us, and if we get any other feedback from folks that joined us. So thanks so much, and have a great day, everybody.